All right, this is a long chapter, but we are at the end. All right, so we've got polarity of molecules. So let's get into it. So this is gonna take a couple ideas we've talked about already and fold them together. So we're gonna talk about the shape of the molecule, and we're gonna talk about the polarity of the bonds, and that's gonna help us determine if the molecule itself is polar or not. So just because there's polar bonds, it turns out, doesn't mean that it's a polar molecule. So we have to be very careful here. So first off, let's just talk about this. So we've got, I just grabbed this marker out of the thing and it is terrible. All right, let's try another one, shall we? We've got by the way, that's top quality editing, right? Like, I just don't do it. Non-polar molecules. You guys get the completely unedited show here. So, non-polar molecules. What does that mean? Well, it means that we have even electron sharing throughout the molecules. There's no uneven electron sharing across the molecule. And what we say is there's no net dipole. So there's no partial positive, partial negative region of the molecule itself. That just doesn't happen. So it's neutral throughout. Okay, so what does that mean for polar molecules? And we're going to really focus on that term dipole more in a little bit too. Polar molecules. Well, that must mean that there is uneven electron sharing. And so that means that there are areas of partial, that's what these deltas mean, partial positive and partial negative charges on the molecule, which means it has a net dipole. Two poles, one that's partial positive, one that's partial negative. That's what we're talking about with dipole. Alright, and so let's draw an example here. This will be a polar molecule just right off the bat. HCl. You dissolve it in water, you get hydrochloric acid. If you don't, you have a molecule, hydrogen chloride gas, typically. Nice yellowish brown cloud of death coming at you if you ever see it. Alright, so what does it look like? Well, hydrogen's going to make one bond, chlorine also is only going to make one, but it has 3 lone pairs. And chlorine is much more electronegative than hydrogen. And so we can label this bond, and really the whole molecule, because there's only one bond in it, as having a dipole. So this is a dipole arrow. Right? And this is a polar bond because it's 2 nonmetals that are mismatched. The less electronegative element is going to be more positive, so you have an arrow with a positive tail. The more electronegative element is where the electrons are going to move towards, so the arrow points that way. That's how I always think of it. And we can see that if you look it up in your book, or you just kind of glance at the periodic table, hydrogen is less electronegative than chlorine. Okay. So, this is a polar molecule. It has a net dipole. It means I can draw this dipole arrow and it doesn't cancel out with another one. So what do I mean by cancel out with another one? Well, I'll get there in a little bit. Let's look at, actually we'll do that one next. So we'll look at CO2. There's our Lewis dot structure. Are these polar bonds? Let's start there. Are these bonds polar? The answer is, yeah, they're mismatched, so they're polar. Oxygen is going to be more electronegative than carbon because, look where they are on the periodic table, oxygen's to the right. It's going to be more electronegative than carbon. And so, electrons are going to shade towards the oxygen. But guess what they're going to do over here? They're also going to shade towards that oxygen. And if I add these 2 dipoles together, and equal in opposite directions, they zero out. So there's no net dipole. Non-polar. Now this is a linear molecule. 2 electron groups, right? Double bonds, single bonds, doesn't matter. That's electron group, that's electron group. There's 2 of them. They spread out as much as possible, 180 degrees. So they are directly opposite each other. Dipoles cancel out. Now if I compare that to, say, H2O, remember this was a bent. So this was about, I think, 104 degrees on the bond angle. So they're not 180, it's a bent geometry because of those 2 lone pairs right there. So when I draw my dipole arrows, they're not directly opposite each other like CO2. They're bent, so they don't cancel. We get a polar molecule. So it's tricky. You got to pay attention to the shape. So, one more example here before I kind of just break down the general ideas of it. Let's look at O2. Is that a polar bond? Or is that double bond polar? No. That means there's no dipole. Which means non-polar molecule. So, if your molecule is just made entirely out of non-polar bonds, it's going to be a non-polar molecule. If it is made out of polar bonds, it might be a polar molecule, or it might not. Something to keep in mind. And generally, if you see something that's made out of all carbons and hydrogens, that's considered a nonpolar molecule as well. All right, so make a note of that. So things like CH4, C2H6, anything like that. If you only see carbons and hydrogens in the formula, it's a nonpolar molecule. So here's the takeaway, right? I just threw a lot at you. You'll probably want to kind of look that over again. Like I into the chapter, you probably cooked, but I like to kind of break it down to something simpler, if not at the beginning, than the end. So polar molecules. And then we got nonpolar molecules. Kind of like how we started. Okay. Well, polar molecules mean that there's a net dipole. And here's how I like to describe it. That means that you have asymmetric polar bonds. Okay? That means that they're not all directly opposite each other. They don't sum to zero. There's something like that bent molecule. Or like HCl, where there's just one. There's no counter because there's no other bond to counter it. So that's an asymmetric polar bond. Nonpolar molecules mean that there's no net dipole. Put the dash in the wrong spot. Actually, I don't have a dash in there at all. I don't know what I'm doing. That's because it's supposed to be over there. Into the chapter. All right. So there's 2 situations here. It means there's no polar bonds at all, or there's symmetry. So you have something like O2, there's just no polar bonds, or you have something like CO2, where they cancel out. Something like that. You get a nonpolar molecule. So you can have a nonpolar molecule with polar bonds, but they all have to cancel each other out. If they don't, they're asymmetric. You have a polar molecule. Alright, so we did a lot this chapter. In the next one, we're going to build on this idea of bonding even more. But for this week, this is a lot to really work through. Some big ideas here. You know, we've really delved into ionic versus covalent even more, and we've talked about bonding structures and how we represent them with Lewis structures, using formal charges to make sure we have the best Lewis structure, especially for when we can have an expanded octet. And then on top of that, like, that's a lot of work already. We've just thrown on the shapes of molecules, and then how that helps us determine if a molecule is polar or not. So when I'm talking about this symmetric or asymmetric situation here, that's 100% tied into the shape of the molecule. You know, linear versus bent, not symmetric. Symmetric. You could have, you know, you could have the square planar. If they're all polar bonds, they're going to cancel out. They're symmetric. But if, you know, if you have another situation where you have like tetrahedral, but only two of them are polar bonds, they don't cancel out. They're not going to sum to zero. They're going to have a net dipole. So there's some tricky ideas, especially at the end of this chapter, where it's really pulling stuff from earlier, putting it together to be a new idea. So, you know, as always, if you need help, just let me know. I'm happy to do that. Otherwise, you know, just keep working, and hopefully, you know, you're getting comfortable with these ideas. So we've really come a long way from just what an atom looks like. Now we're talking about what entire molecules look like, and we're going to really dive into that next week some more. So these ideas aren't going away anytime soon.